Welcome to ValleyML AI Expo 2021. My name is Tirthajyoti Sarkar. I am the track chair for the AI optimization track. And here we'll start with the first speaker of the day, Jongboom. He's an embedded engineer and machine learning advocate, and he's always looking for ways to gather more intelligence from the real world. Jan has shipped devices, worked on the latest network technology, simulated microcontrollers, and there is also a monument in San Francisco with his name on it. Currently, Jan serves as the co-founder and the CTO of Edge Impulse. Edge Impulse is the leading development platform for embedded machine learning with 40,000 plus projects under their belt. So Jan, please take it away. Thank you.
Hi, my name is Jongboom, and welcome here at our session during the ValleyML AI Expo on running machine learning on devices literally all around us. So, my name is Jongboom. I am the co-founder and CTO of Edge Impulse. We are a startup. We're probably the largest ecosystem of embedded machine learning. So that's machine learning that runs kind of as close as possible to the sensor as we can, and I'll explain a little bit what that is and what the reasoning behind that is in this presentation. I have a long background as a software developer. I think I got my first paid gig as a developer back in 2007. But since about 2013, I've been trying to make devices really understand the real world. And you see me actually playing with a dev board, connecting some sensors. I think this is from 2016, sitting on a terrace in East Africa, trying to get something together for a workshop during Data Science Africa. And as you can see from that photo, I'm an embedded engineer. And the reason that I started doing machine learning is because I felt that ML was a way of actually making the devices that I have understand the real world. So I come from a completely different background, and I think a lot of the theoretical research that is being done, and even a little bit if you look at kind of the hardware that is being presented today, kind of what the background of those people is. So really a software engineer that loved doing embedded stuff that now finds its way as the CTO of a machine learning startup. So if we look at kind of these, I looked at the program today, and these are just, some of the sessions that we see in the parallel track and the AI hardware track. Like, oh my God, there's so much shiny new stuff happening. So we see FPGAs, specialized silicon, new silicon blocks, hardware accelerators, NPUs. All of this stuff is truly amazing if you think about, where we were a couple of years ago running AI or ML on edge devices, and the type of silicon that we now see, specialized accelerators, specialized silicon IP blocks to make all of this stuff run faster. So a lot of really cool and new and shiny stuff. But, and this is me as an embedded engineer speaking, look at the volume of stuff that is already there. Stuff that doesn't have these new fancy FPGAs or NPUs, but look at the volume of devices that have shipped over the last, in this case actually 4 years. It's truly astonishing. So I used to work at ARM, and this is a graph that I stole from their quarterly report. ARM is currently, and that's just one of the kind of IP companies that creates IP to build computer chips. There's 842 chips per second being sold with ARM technology in it. Absolutely astonishing, right? At this point, I think there's 24 billion with a B, chips being sold every quarter. So close to, or every year, sorry. So that's close to kind of 100 billion in a 4-year period, which is insane because it took us from 1991 all the way to 2017 to get to that volume, and now we're doing that in 4 years. And a lot of these devices are not, large computers with GPUs attached or specialized silicon to do quick machine learning operations, but rather like 65%, and that's the ARM case actually, of these are microcontrollers. And if we talk about ubiquitous devices, like in the title of the talk, then microcontrollers are definitely there, right? Microcontrollers are slow. Okay, fine. They're maybe 100 megahertz max. That is actually pretty fast already. They come with limited memory, 256K of RAM is actually a lot. A lot of these actually come with a lot less. You might think, okay, well, yeah, sure, these are ubiquitous. There's billions of these being shipped every year, and they go into all kinds of products from, like AirPods, for example, you put in, there's probably a microcontroller in there, to your piano or your car, where there's more like 60 of them in there. So I understand that these are ubiquitous, but like, what can they actually do? Like, they seem so incredibly limited when we talk about machine learning, or we often talk about, large clusters of GPUs crunching numbers, or specialized FPGAs that can do these inference multiplications much faster. They have a couple of benefits, right? The first one, maybe the most important one, is that they're very close to the sensor. If you're collecting data from the real world, then there's probably a microcontroller attached to your sensor at that point. So if you want to do something with that sensor data, you don't need to offload it anywhere, you don't need to send it anywhere. You can process it directly where you collect the data, and that has a whole bunch of really cool benefits, right? If you don't need to ship data off, it means you don't need to pay for transport, you don't need to pay your telco bill, you don't need to pay a cloud bill to actually process all of the data. And this is the cool part, and I don't think a lot of people realize that, and this is what we're going to be talking about a bit more in the next 15 minutes. They're much more capable than you'd actually think. You think, okay, this like little piece of silicon, you see it in the red box here on the left, like how capable can it be? Well, actually tremendously capable. So let's dive into that a little bit. So coming back to Edge Impulse and why I think this is interesting, well, for me, the interesting part of machine learning is not the algorithms, it's not the models, but rather I have a sensor and I have a microcontroller already. They're currently collecting data, and now I want to do something with the data. And the only place for me to make logically sense is to be as close to the sensor as possible. So 2 years ago, a little bit over 2 years ago, we founded this company. From engineers, for engineers, we say, we make a product, Edge Impulse Studio, that helps you every step of the way from data collection to deployment, and really have kind of a data-driven engineering workflow for dealing with sensor data and finally deploying that to the sensor edge. We have an amazing community of customers, but also just developers that build stuff on top of Edge Impulse. As of today, there's over 40,000 real ML projects already created. So pretty insane. And I'll go into a couple of examples of stuff that people have built with this stack. So the type of application that people build kind of always rely on anything with messy and high resolution sensor data. So I like to think here not about the type of model that you want to run, or how do we scale down this super large model to something that is small enough to run on a microcontroller, but rather first think about the use case. So what do you want to do? Maybe recognize sounds. So that could be anything from wake word detection, hello world, or okay Google, to detecting audible events. Glass breaking naturally is a typical one, but also continuous monitoring of a steam pipe, for example. Classifying images. You're not going to run really large MobileNet SSD type or YOLO models on here, but we can actually do a lot already on these MCUs. Biosignal analysis. If you've ever wore a health wearable, there's probably some ML in it to either recognize your activities or recognize your sleep. And we have customers actually doing that on top of Edge Impulse. Or stuff with, for example, vibration data. So am I in a factory? Does this machine vibrate differently than all the other machines in my factory? This kind of stuff. So sure, microcontrollers are ubiquitous. Great. You can trust me on that. Yeah, these use cases all sound really cool, but how do we do that? So given kind of the type of people that are watching this, I'm going to skip over just the basic stuff, like, we only do inference, we do quantization, we do pruning, etc. If you're more interested in that, cool, just shoot a question in it, I'll talk a little bit about it. But let's actually look at the stuff that makes this uniquely possible on a microcontroller. So the very first thing is, I think we need to realize that on-device intelligence is not new. And on-device intelligence on sensor data is not new either. We just used to call it signal processing. Much more deterministic, right? Rather than training a model, we just have rules. And signal processing still is an amazing place in a machine learning pipeline for embedded systems. So what can signal processing do? So here's some accelerometer data, and it's incredibly noisy. Now, a machine learning algorithm, a neural network, can probably learn what this is and denoise and kind of fit all of that into a large neural network. But here's a little trick that signal processing can do. Apply a low-pass filter, bam, now I have clean data. And thus, the job of our machine learning algorithm can be much, much easier. And this is something we see much wider. So the first step that we do, if we look at sensor data, and we try to help you model this in Edge Impulse easily, is, well, first, let's see how far we can get with ordinary signal processing. And that means that any feature that you extract there is one that a neural network doesn't need to encompass. Neural networks can basically mimic almost everything, right? This whole signal processing step, that could be something that the neural network can learn, but it requires a lot of capacity and a lot of training. And signal processing is both deterministic and relatively fast. So we can significantly reduce the number of input features, leading to smaller networks and a lot less noise. So it cleans up the input. Just an example, like this is a data set of me doing three things: fist bumping, moving up and down, and drinking a beer, collected on the accelerometer. Now on the left, you just see raw data. And you can actually see sort of these motions already, right? So drinking beer, there's a lot more motion on this axis. Up and down, there's a lot more motion here on this axis. But if you look at a single one of these little balls, you couldn't tell which of these it really belonged to, right? Because if you look at all of them, it's kind of possible, but not if you look at a single one. If we just do some signal processing, so this is just an FFT over this data and then looking at where the energy is, it actually separates much nicer. So a machine learning algorithm can just basically do a logistic regression over this and be done with it. So really cool. The second thing is that you want to design in a place where your constraints matter, right? So your microcontroller is limited, okay, fine. But as long as you use that from the very first moment that you start designing something, then you're not going to be in this area where you just try to scale something that works down to something that works, but you're just designing something that will fit from the start. So take a look at how much RAM and how much flash do we have available. Take a look at the sensor suite that you have. What is the frequency that we have here? What is actually the frequencies that we can use to still hit our RAM, flash, and power budgets? Then look at kind of how often do you want to have this inferencing run. Probably not all the time, because then you burn through your battery really quickly. What is actually the target number of inferences per second? Can you actually wait 10 seconds before you do something? And then finally, some hardware acceleration. Can we actually use that? And what effect does it have on everything here? And once you have those constraints and you've modeled them, and you can visualize that every step of the way for the people building these algorithms, you're never going to run into this issue where you try to scale something down. So the way that we try to do this is that we show these constraints directly the moment that you interact with a model. So a pre-processing step could be, I have audio, like a keyword, and I want to turn it into a spectrogram. And that spectrogram is it highlights the interesting frequencies. It has separated frequency and time domains already. It has removed noise, and that's something I can pass to the neural network, which can do this job much faster. But there's many constraints here, right? When I'm designing that spectrogram, like what should the fast Fourier transform length be that I want to use? Well, like for example, I have a choice of 128 and 256. It doesn't really matter what these numbers are, right? But both of these have an impact on inferencing time and the RAM usage of my device. And it might very well be that only one of these actually fits. So maybe the FFT length of 256 yields a 1% point better model, but it also adds about 100 milliseconds per inference. Can I actually use that, yes or no? The same with neural networks, right? So if I have a keyword spotting model, I can attach a 1D convolutional neural network or a 2D convolutional neural network, but both of these have a drastically different impact, both in latency and in memory usage. So what we've done, I think is pretty cool, is that we modeled all of the fully supported hardware in Edge Impulse. So we actually know how fast it's going to run and how much memory this is going to take. And thus we can directly show you, whenever you're building this model, exactly whether this is going to work, yes or no. And thus, save you a whole bunch of time in designing stuff that is actually too big to actually fit on device. And we're taking this one step further. This is really cool. If you ever done anything with sensor data, go take a look at what we released a couple months ago. The EON Tuner takes us one step further. So this is our AutoML pipeline specifically for sensor data. So the interesting part of sensor data, especially if you look at the pre-processing pipeline, is that there's a lot more options, right? All of a sudden I have all my pre-processing blocks that I can fill in with all of those parameters. And maybe I want to downsample my data, which will process faster, but will remove some of the information in the signal. And then we have the neural network, etc. So it's a really big search space, much bigger than you have if you just do AutoML in your neural network. But because we have really accurate modeling of how fast this will run on your target device, we can kind of offer this in one go. You say, hey, this is the problem I'm trying to solve. It needs to run on this and this device. These are my constraints. Okay, go find me the best model or a number of candidate models, as you see here, a number of candidate models that will actually give me good performance and will fit on my device. And how you kind of split that up, that is up to you. So accurate modeling really helps kind of in here. We first expand the search space because we have so many more parameters, but then we reduce immediately to just show stuff that will run on device. The third is to realize that microcontrollers are actually not that slow. So these pre-processing steps, those require stuff like FFTs, filtering, and on neural networks require things like matrix multiplications. That's in essence everything that the neural network does. And those are two things that MCUs are actually really, really good at. Because signal processing is not new, so these MCUs typically ship with either onboard with an external DSP or with an FPU, which can kind of do all of these kind of pre-processing steps. And most of the modern MCUs actually have vector extensions, so they can do these kind of vector operations, matrix multiplications, really, really quickly. So by using these hardware acceleration, like from the get-go, there's very good libraries typically from vendors these days. You can actually make these operations really, really fast, like 7 or 8 times faster as you could do in software. Then fourth step that we do is that if you look at kind of where inferencing engines or, inferencing engines kind of came from, let's say that you're running a Python model on your desktop computer. So how will you do it? Well, you first instantiate the interpreter, for example, TensorFlow. Then you load a model. Then it builds a representation of that model, and then you execute them. That works really great on desktop computers, even on GPUs, on mobile phones. But it's kind of a waste on embedded systems, right? Because you need to ship the interpreter. Thus, you need to ship all the potential state that the interpreter might run into, like all the operations, layer types, etc. And you have kind of this overhead of first loading that model, and that takes some memory as well. So the thing that we shipped recently is the EON compiler about a year ago. So what we do there is we say first we convert your model into source code, and then we just let the compiler do its job. So then you lose the interpreter, you lose anything that you don't use, which is really great. So very big memory savings and flash savings. And last, because of this, we have full freedom in kind of how we put everything somewhere on your MCU. So if we know your target and we know you have fast RAM and slow RAM, we can put your weight somewhere and your scratch buffer somewhere else, etc. So be much more flexible. So just some numbers here. Compared to TensorFlow for microcontrollers, on keyword spotting models, we see about 35% less RAM and 38% less flash. Really great, because those are really expensive things on microcontrollers. And on image models, we see a similar saving. So about 32% less RAM running MobileNet V2 with a 0.35 alpha on a DSP. So let's show some cool stuff that people have built. If you want to see real solutions and real stuff in the field, I'll have a link to that. But for me, the interesting part is not what our, well, sort of, like, yeah, what our customers are building, really important, really awesome, but I'm much more interested in what the community can build. Because if we put these tools into the hands of ordinary people, that's where innovation comes from, right? So here's 3 quick demos of stuff running on microcontrollers.
Microbit. Hallo. Microbit.
Really cool. Running on a Cortex M4 at 64 megahertz. Here's me. Christmas tree, not Christmas tree. Christmas tree, not Christmas tree. Running on an ARC DSP at 400 megahertz. So even computer vision models, relatively constrained, but we can still run those. And maybe the coolest of all, Benjamin Cabet actually made the cover of Make magazine back in May with his artificial nose. Really simple device with a gas sensor, I think maybe two types of gas sensors. And he trained it on smelling all kinds of booze, smelling all kinds of baked goods, etc. And that runs fine on a microcontroller as well, relatively low resolution data. Really cool. So, okay, I hope I gave you a bit of a glimpse into what is possible with microcontroller devices today. If you want to get started, that is really the best way of actually exploring this yourself. Head to edgeimpulse.com/docs. We have a very wide range of dev boards from Cortex M4 to even like larger GPU things if you want to do object detection. You can deploy to any device that has a C++ compiler. So if you have a brownfield device, go use it. Or even use your phone if that's more your thing. So let me recap and then we can go to Q&A. First of all, the ML hype is real, right? Okay, yeah, sure. We're here at ValleyML. Great. We're at a thing called the AI Expo. Sure, you know this. But it's sometimes hard to kind of see what is really possible through the hype. And what we've seen in the last 2 years with Edge Impulse is that machine learning has really gone from, oh, this is a really cool idea, to something that we see that is actually changing products now. And I think that is a really, really exciting time to be in. The second thing is that if you look at where to deploy machine learning, deploying it close to sensors, that is a really perfect fit because sensors generate lots of really high resolution, messy data. And offloading it to the cloud to process is almost never a feasibility. And last, it's really hard sometimes especially if you're in a conference like this, to kind of get super excited about all the new stuff that is coming. But I'd like to actually make you think about the billions of brownfield devices that are out there and the 180 billion chips that have shipped already. Let's take a look at what we can do actually there rather than ship completely new silicon. So with that, I want to thank everyone for being here, and we'll switch to Q&A right now.
So I'm actually seeing 2 questions right now on our chat, and then questions will flow in. So I think one of the questions that I'll start with, we have Arpit kind of talking to us about, hardware deployment is an art. How should a beginner start in this domain?
Oh man, do you have minutes? Yeah. I think you guys are veterans in the semiconductor industry as well, right? Like this used to be much, much harder. So what I really like about stuff that has come out in the last, 5 years or something, maybe a little bit with the advent of Arduino and the way that they push the ecosystem forward, this is a lot more kind of development hardware that's very close to final products, right? So these days I can go to almost every silicon vendor and say, hey, I want a dev board that has a processor that's fast enough for me to run some of my ML stuff. It needs to have integrated managed microcontroller or managed microphone, which is also truly amazing technology, right? I can get a microphone this size package. It's absolutely incredible. Yeah. And very often, even with stuff like LiPo connectors, so I can actually just put a case around it. So I think that's really cool. My suggestion here, if you really want to start, take one of those dev boards. Like take an Arduino Nano 33BLE Sense, for example, really nice little tiny board. Start working on that and do it the same way that I did my first product. Like literally just solder a battery to it and there we go, very first product. Like going from 0 to 1 has been made tremendously easier. From 1 to 1,000, still really, really hard. But take the stuff. There's now modules for virtually everything, which makes it a lot easier. Stuff like your RF certification, you can kind of offload that to the module manufacturer. So there's a steep learning curve, but it's a doable learning curve. And especially when you're testing something out, it's much easier than it used to be. Awesome.
Love it. From 0 to 1 and then 1 to 1,000,
There we go. And then to 1 million.
Awesome. Yes, exactly. Okay, great. So we have another question. How much compute do you actually need for apps? For example, keyboards, keyword spotting or computer vision?
So less and less, right? So 3 years ago or something, when I first got into the field, computer vision, you really needed a Cortex-A, like an application processor, NPU type device, and preferably even a graphics card, right? Just to do some inferencing over that. That has gone down so fast, so fast. So in the talk, I did a little demo of Christmas tree detection, which is actually, it looks a bit silly, but it's actually something that's super valuable even in industrial use cases, because very often you have a very constrained problem. It's just, do I see the screw being screwed in, right? Yes or no on a factory line. And we can do that kind of stuff on Cortex M7, microcontroller, or even a DSP, which is truly amazing. And that's kind of the upper end. And then Cortex M4, so typical $2 microcontroller, can do real-time audio interfaces now, and Cortex M0 or even 16-bit MCUs can do vibrational analysis, and that is coming down quickly. So at our own conference, Imagine, we showed our first object detection pipeline that's running on MCU. So really on 11 frames a second on a DSP doing real-time object detection, which is, man, I never thought I'd see the day.
So. Yeah, that's awesome. That's awesome.
Like,
okay, great.
Progress, right? Because then you never think, and then in 3 years it happens, kind of.
That, man. So like in 2017 or so, 2017, I was in a bar in Taipei, and one of my colleagues at ARM like walks up to me, and he's like, "Oh yeah, so it works on this little thingy, and it lets you run neural networks on a microcontroller." And it was this is literally just MNIST, right? 28 by 28 pixels. I was like, wait, this changes everything.
This is starting of an era, right?
And just knowing that it's possible, and then you start unlocking everything and realizing that that you can do that, and that's where the magic really starts.
Yeah, absolutely. Great. Okay, we have one more question so you mentioned about modeling your hardware is important, right? But how do you accurately model your hardware?
So we use a variety of techniques. So there's kind of 3 things that are important for hardware modeling. One is latency, right? How fast does this run? And that's really dependent on the underlying hardware, because some hardware might have vector extensions, or it might have a DSP that's really good at vector math. So to do that, we use a variety of techniques. So we use fast models. So that's commercial software from ARM that can accurately model physical hardware, and it's very flexible. So you can configure clocks and RAM speeds and stuff. Then we use Keynote, which is open source ARM hardware emulation. So that's kind of for all kind of stuff where we don't have fast models. Together we kind of built a model every single dev port that we fully support of like how fast is a typical DSP and neural network operations. And then for memory, we just compile down our stuff. We basically statically allocate all of the buffers that we're going to need, and now we know exactly how much memory is going to take on the device. And we're working on some stuff for power consumption, because it's also it's critical, right?
Absolutely. It's great to see that you're looking at all these different areas.
I mean, how many compute versus power you want to run an optimization, then you can model both and then get the answer.
So
settings.
I think especially if you talk about battery power devices, it's a really interesting trade-off that you can make, right? So I know that if I run my model, like I'm doing keyword spotting or something, I run pipe monitoring or something in a factory, I can run my microphone all the time and run inferencing all the time. But that means I need to run my microcontroller in high power modes. And what does it mean if I would only sample every 10 seconds? Would I miss events? Right? How can we model that kind of stuff? And what is the effect on power consumption? That's the stuff that we now want to build and really have. And how cool would that be, right? So you can actually you see the trade-off, and we'll help you design that.
And the as you mentioned in the first question about the workloads, like image computer vision, they're kind of always hungry for more power. And kind of them sitting in a smaller and smaller form factor. How do you make sure that you're modeling the right workload on the right hardware?
And this a little bit where we've started a little bit on this, but not as far as I think we can go. But sensor fusion for this kind of stuff is really interesting.
Oh, yeah.
What would it mean if I have a motion sensor and a camera, and I have data from both? What is the effect on my accuracy of my model if I need a signal from a motion camera before I actually snap a photo? Is that going to add too much latency? Yes or no? How do I model that? But it has a tremendous effect on power consumption, right?
Right.
So if you can model all of that, that is, yeah, it's not even ML model building, it's application building, but I would love to model all of that.
It's the scenario by scenario analysis in the business settings, industrial settings, consumer settings. Different things will have different weighted there, and whatever makes sense, right? You have to optimize
Exactly
for your customers.
Yeah.
Okay.
And,
So we
last point. Oh.
Yeah. Go ahead.
I know. Yeah. So here's the interesting thing, right? Model accuracy doesn't tell me shit, right? 94% model accuracy. What does that mean?
Yes.
Right. So for us, kind of this post-processing stuff is what we're building now. We're going to release it next month. Is what is important for you, right? If I have a keyword spotting model, it's fine if it doesn't wake up sometimes, and it's really annoying if it wakes up all the time when I don't say the word. If I have a fall detection system, it's really annoying if I fall and it doesn't register. That's kind of death of my product. And the other way around, I can kind of correct it. So this kind of stuff, like all this post-processing and balancing, I think there's so much more to win, and it's been neglected a bit by the ML community. But it's just
for all the data science people who are attending. Jan is literally saying hardware, how to do the 2x2 confusion metrics you may have to do in your projects, how to reduce that confusion using hardware, right? He's just describing that. Okay, I think great. It has been great. So Noit, go ahead.
Yeah. I think we are right on time. So I think very much, we kind of covered the whole scope, starting from how you start, kind of how to think about performance and the correct modeling. And this has been great. I really, thank you, Jan, for your time here.
Thanks, Jan.
We'll continue to attend more sessions in the conference.
And for attendees, please don't forget to go to the next session, and we'll start the next question and answer session again around 5 to 6 minutes before the next session ends. So please go ahead and head on. Thanks, Jan.
Thanks, Jan. All right, thanks.
Bye-bye.
Bye.